show the robot one or more times how to do it properly, again and again, and presumably now the robot has some amount of memory, so it's going to try to replicate that behavior. But the human behavior is not perfect. He didn't do the exact same motions all 3 times, so the computer, the robot, needs to infer. And so after 3 times, 5 times, this is not how you flip a pancake properly, but the researcher or an assistant is probably off camera, either giving a +1 score to the robot or a -1 score, because the robot's then going to want to do more of a +1 and less of a -1. So a system of rewards and punishments virtually, if you will. Now it's getting better after 15, after 20 trials. It's still not perfect, but you'll see here that it's hopefully learning. And here is just another angle that shows you how these physical motions really just reduced to math, some geometry on the screen, up, down, left, and right. And now the robot is indeed flipping that pancake better and better. And if we keep going with more and more trials, it should be able to repeat that again and again. And here we are from the first angle after 50 attempts. Now it should pretty much get this right again and again. And funny enough, this probably is not unlike how we humans, how a child, how a chef learns to do something. You keep practicing and practicing and practicing. And if you have someone there, especially telling you like good job or bad job, hopefully you do more and more of a good job effectively learning in this way. So now when we consider not pancake flipping, not game playing, but some of today's problems that intersect with tools like ChatGPT and the like, let me propose that we consider what's called nowadays deep learning, where you really just feed the computer lots and lots of data, so much data that you don't have time, you don't have the resources to pay a human to teach the robot. You just want to feed it lots and lots of data and let the computer find patterns, figure out how to solve certain problems. And so, the term of art that you might see tossed around in this space are what are called neural networks. And long story short, for today's purposes, neural networks draw inspiration from how we humans think the human brain currently works, where you have lots of things called neurons. They might look a little something like this, blown up to scale, and they have some kind of electrical interconnections that can transmit signals from left to right, top to bottom, and so forth. And if you have enough of these neurons, it turns out you can effectively use them to implement math and represent information. Like here's how you might connect 2 neurons. But honestly, this isn't a biology class. This is a computer science class, so let's abstract this away as we often do. Here are 2 neurons, but just with circles, but some edge between them. So there's some form of communication, not unlike today's networks. And if you now have 2 of these neurons on the left and 1 on the right, you can imagine using this to implement a problem to be solved, where you have 2 inputs on the left, and you want to figure out what the output is on the right. Let's try something simple. Here is a very contrived world in which you have an XY grid, vertical and horizontal here, and suppose this world is filled with blue and red dots. And you don't know what makes a dot red or blue, but if you show me enough red and blue dots, I bet I can start to figure out or infer, either as a human or as an AI, whether a dot, given its x and y location, is going to be red or blue. Well, how might I do this? Well, I could start simply here on my xy grid, and I could just propose that if I wanted to give as inputs to this problem an x coordinate, like a number, a y coordinate, a number, I want to get back an answer red or blue on the right. Well, the simplest way to do this, honestly, is just to kind of ballpark it. Okay, it looks like I can draw a white line there, and anything to the left is going to be blue, apparently, and anything to the right is going to be red. Now, that might not necessarily hold true with more data. So the more training data you have, you realize, oh, darn it, I need to adjust my line. So for those of you familiar with math or statistics, try to find a best fit line for this data. All right, so let's try a diagonal line instead. Let's throw some more data on it. This line looks pretty good. And unless I want to start getting in like some parabolas in there and x squared and y squared and sort of fancier math, this is a pretty good line because like 80%, 90% of the time, the computer, or me, the human, is going to be able to predict red or blue correctly. And so what's really happening here is we really need to figure out what the mathematical formula is for that
explanation.
What is the x, the y, the a,
Difference
the c,
with our era.
And again, this is as mathematical as we'll get today. You're essentially trying to figure out dynamically, through trial and error, what is this formula? X and Y are the actual coordinates of the dots, but what is A, what is B, and what is C that makes this formula work? So that if the answer is greater than 0, let's call it red. If the answer is equal to or less than 0, let's call it blue. Or you can flip that, it doesn't matter. But what you're trying to do through more and more data is infer what that math function is. And in practice, it's not as simple as 2 dots on the left and 1 dot on the right. You have multiple layers, and so the mathematical formula that AI software is coming up with is much more complicated, so much so that if you ask even the smartest engineer at Microsoft, Google, or in the real world, they can't even tell you what most of those dots represent, because it's just something the computer came up with as sort of a best fit attempt for that data. We might understand the inputs, we might hope for the outputs, but even we humans don't necessarily understand how all of this is working. And yet it's so darn powerful. You can feed to a computer nowadays lots and lots of examples of like human written numbers, 0 through 9, and the computer can effectively, given enough data, figure out how to get from a handwritten 8 to a virtual version of 8. And how might it do that? Well, here's a really big neural network, and every one of these dots on the left, there's 784 of them, represents a specific square in the square at top where the human has written some letter. So you can represent each of these dots as maybe it's black if it's blank, white if there's actual text there, and given those 784 dots that can pose any number, you can ideally figure out that, you know what, that looks with high probability like a 2. And that brings us lastly then to these large language models, and CS50's Duck, it's almost like ChatGPT. They too are leveraging exactly those principles of using large amounts of data to learn deeply on. They are using neural networks to kind of figure out what the patterns are in all of the English words and sentences in the world, all of the Indonesian words and sentences and paragraphs in the world, figure out what those relationships are, so that when you or I type a question in, they can sort of traverse that whole neural network and figure out with high probability when I